I think we might be live. Great. Welcome, everyone. Thank you for joining us for today's lawphysics webinar. My name is Alejandro, and I'm going to be your host today. We're presenting a cartography of spacetime around supermassive black holes by Pau Amaro Seoane. Pau works in many areas of general relativity and astrophysics, including nonlinear dynamics and gravitational waves. Pau did his undergrad in Valencia and then moved to Heidelberg to do a master's and then a PhD in theoretical astrophysics. Then he went to the Max Planck Institute of Gravitational Physics in Potsdam, and I believe that's also named as Albert Einstein Institute. And he worked on gravitational waves where he was a senior scientist until 2016. Then he went back to Barcelona with a Ramon and Cajal Fellowship, and now he's currently a fellow of the Institute of Multidisciplinary Mathematics at the Technical University of Valencia. Remember that you can ask questions over email, through our YouTube channel or Twitter, and then the questions will be read at the end of the talk. So now, without further ado, we will turn the time over to Pau, and thanks for joining us. And Pau, thanks for giving this lawphysics webinar. The floor is yours.
So, first of all, I'm being forced to speak in a non-Latin language, in spite of being the Latin American webinar, which is not my preference, but anyway, let's go. I'm going to share now this PDF, and I hope that you can see everything, Alejandro.
Yes, perfect.
Maravilloso. Bueno, so usually I like to ask a lot of questions when I am giving a talk, but this is supposed to be a monologue, so that I'm going to try to do it as interesting as can be. So when I say a cartography of a space-time, I mean it. I mean, it's like making a map around an area which is not accessible to us with light. I mean, via our old friend, the photon. And I'm going to explain what these extreme mass resonance spirals are. So, first of all, I cannot, okay, yes. People in astrophysics like to talk about high energy phenomena. And this is something that I find funny. Because, so, first of all, when the first gravitational wave was detected a couple of years ago, it was announced during the press conference by Kipthorne that this corresponded to a system of two black holes with masses of about 30 and 30 in spiraling around each other. And when you calculate the total power output of these two stellar mass black holes merging, which is what I call here weak sources. I don't know whether you can see my cursor, but this is on the title, weak sources. We can. Wonderful. So when you calculate the total power output of these stellar mass black holes, it turns out that it's greater than 50 times all of the stars in the whole universe put together. Of course, I am cheating a little bit because I'm talking about the power, right? Which means that we are dividing by time, and this was a very short event of about 20 milliseconds. So you get a very high power. But still, if you only take into account the total energy released, this corresponds to putting 3 suns, and remember that one sun is about 100 times, if you want, the size of Earth. So you take 3 of them, you convert them entirely into energy, and that perturbs what we call space-time. And this is transmitted as waves, and they reach us. So you need a lot of energy to perturb space-time. And the interesting thing about these waves is that they contain a lot of information, the same way that with your smartphone, you receive emails from say that I get an email from Alejandro, and he sends me a picture of his girlfriend or whoever. That information is encoded in a radio wave, which is getting to my cell phone. In that wave, I have my password encoded. I have the picture of Alejandro's girlfriend encoded. And all of that is captured by my device and translated into information that I can read. In the case of gravitational waves, we have something similar. We have a way to finding out what space and time are around supermassive black holes. But this is something very important because usually light does not allow us to get to the very, very small and long distances. When I mean small, I mean I'm talking about the size of the astrophysical objects. And the light does not allow to reach those very small, tiny, small astrophysical objects at huge distances. Because in space, we are human beings, we light and enjoy light. This is why we have developed eyes. The light that gets to us is being absorbed a lot in its travel towards Earth. Now, the first wave that we detected, which is named GW150914, just to give you an idea, this was around the corner. So from a point of view of gravitational wave science, the distance was very, very, very short. And nevertheless, if you translate that distance into time, these two black holes merged back in time when life here on Earth was starting at a cellular level. So it's been a while. And nevertheless, from the point of view of gravitational wave astronomy, as I was saying before, this is really around the corner. Anyway, so if you make this is a fun exercise. If you convert this into energy, this corresponds to about 3 times 10 to the 54 tera electron volts, which is a lot. Anyway, when you go to supermassive black holes, and these are what I call the strong sources of gravitational waves, when you have a binary, and I'm talking about binaries because you need a quadrupole, which is so you have to perturb the space-time the same way that, for instance, when you throw a stone into a pond or a swimming pool, that stone, perturbs water, and that perturbation is transported like a wave. Now, in order to perturb space-time, which you can think as like water, you need a lot of energy. And and that stone that you're throwing into the water is in this picture are these two compact objects orbiting very, very fast, accelerating actually around each other. Now, when you take into account, instead of having 30 and 30 solar masses black holes, if you had 100 million plus 100 million solar masses black holes, and these we know that they are very common in the universe, you would be putting into pure energy something like 5 million of suns, which corresponds to about 10 to the 60 tera electron volts. So this is real high energy astrophysics. So I'm going to just talk about the different kinds of black holes that we think that we have in the universe. We have stellar mass black holes with masses ranging between 5 and a few tens, and this was actually a big surprise because LIGO, the first detection, as I was saying before, announced a detection of about 30 solar masses, and we still do not know how to form from the point of view of stellar evolution a black hole with a mass of above 10 solar masses. I mean, when I say stellar evolution, I mean orthodox evolution. And these you find everywhere in the galaxy. Then we have supermassive black holes with masses ranging between 10 to the 5 solar masses and a few 10 to the 10 solar masses, which means 10,000 millions of suns. And we find them in galactic nuclei. And if on the one hand you have something tiny, like a baby, and on the other hand you have something, large, like an adult, it stands to reason that in between you should have an intermediate range, which is why, being extremely original, we call this range the intermediate mass range. Black holes with masses between 100 and 10 to the 5. There's a lot of debate about them, and I will not talk about this today. Anyway, so what do we know about black holes? First of all, general relativity predicts them. We have the singularity theorem, to whom the Nobel Prize was awarded last time. We have trapped surfaces. There are some physical phenomena that can only be explained via these black holes. We have a long list of indirect observational indications, and we have probably an even longer list of theoretical motivations for their existence. And this is a very usual and common situation in science. So why do you need such long lists? This is a question that I very frequently ask the students. You need such long lists because you do not have direct evidence, right? At this point, they say, yes, you're right. We don't have a direct evidence. And I say, wait, what about this? This is the first detection of a gravitational wave of the first system that I was talking about. And we have the signal in Hanford and Livingston, and this is, anyway, this is the strain, which means how much can you stretch or compress the laser beam because of that gravitational wave, and you see that it's dimensionless. We're talking in units of 10 to the minus 21, and LIGO has a length of a few kilometers. So it's a 10 to the minus 21 part in a few kilometers. And here we have the time in seconds. And when I showed this, then the students, they shut up and say, okay, we have evidence that black holes exist. And then I go and ask the question again, do we really have an evidence that black holes exist? Because there's a problem. There's something called signal-to-noise ratio, which means something like how well can you measure the signal given a detector, right? If you have a crappy TV antenna, the series on your TV will look very bad. If you have a very good antenna, well, the resolution on the television will be very good. And that's the equivalent to signal-to-noise ratio. And this corresponds to the first signal, as I was explaining before. And the first signal had a signal-to-noise ratio of about 25, which was a lot. But the problem is that you have to get here. You have to get to the very late ring down in the event, because there are 3 different phases. I don't want to get into details, but you need a lot of signal-to-noise ratio to get into what would be a very strong evidence that these systems are black holes and nothing else. And I don't say proof on purpose, because in physics we don't have proofs. We just have, more and more strict tests of our theories. Anyway, so as a matter of fact, these waves that you can see here can be explained in terms of, for instance, in this paper by Vito Cardoso, they can be explained in terms of wormholes or gravstars. In this paper by Cecilia Chirenti and Luciano Rezzolla, it's not, it's not that they want to prove that the wormholes exist or that gravastars exist. It's that this was a proof of concept explaining that what had been observed is a very robust evidence it's actually a direct evidence, a direct measurement of gravitational waves, but it is not the proof that black holes exist, okay? And it is maybe with the new resolution of LIGO, probably we will make it to the very late stages in the process. But as of now, and to the best of my knowledge, this is still a kind of open question. But there was recently a very nice and spectacular work by Badri Krishnan on the detection of the quasi-normal modes with the open data of LIGO. That paper is wonderful, and I encourage you to have a look at it. So this is a little bit of propaganda. In 2015, and this was also presented 1 and actually 2 years before 2015, with a very good friend of mine, because I like to work with friends, Shan Chen. We predicted that LIGO should mostly be observing black holes in this range of masses between, say, 30 or actually 20-ish up to 100, with low spins, and they should be circular. Now, this is the first detection with masses such as the ones that I have mentioned. Very low spins, but don't get fooled. Look at the arrows, plus minus 48, plus minus 28. And this was detected with circular templates, which means that they were circular. Now, we have an interesting, we have statistics now. This is a graph that the sister of a very good friend of mine, Majo Rosell, Bustamante Rosell, did. And you have here the range of masses. So between 12 and, I don't know whether you can see it, 24, 36, up to 96. And all of them assume having detected with an eccentricity of 0, and all of them have very low spins. So the range of our prediction starts around here. This is only black holes, by the way, and goes all the way up. So I would say that we did rather well with that prediction. Anyway, enough propaganda. So why is this so important? Well, from the point of view of fundamental physics, these detections of mergers, because we have mergers of black holes, but we also have in spirals of neutron stars, which are merging outside of the LIGO band because of, well, I don't want to go beyond 2 hours. So these detections are a prediction of general relativity in the strong regime. This is, if you want, now that it is very fashionable, this is a politically correct way of saying that general relativity should be correct. Secondly, we have a proof. I have written here proof, but again, I don't like the word proof in physics. We have a very robust, evidence that gravitational waves exist, and that objects consistent with general relativity, black holes, are present in the universe, which again is a politically correct way of saying we have detected directly gravitational waves, and that stellar mass black holes should exist as well. From the point of view of astrophysics, although it looks, more modest, it is not. Don't get fooled. We have an evidence now that these dark objects exist, and they have masses larger than the nominal mass of 10 solar masses. I was mentioning this at the beginning in orthodox stellar evolution. Secondly, they form binaries, and third, they merge. Now, what about supermassive black holes? Do they exist? Well, it looks like that. This is a real picture taken from the so-called Event Horizon Telescope. this an incredible effort which has put together a lot of telescopes to observe a tiny, tiny region in a galaxy, actually two galaxies, M87 and our own Milky Way. And I say incredible effort because even when you say a supermassive black hole with a mass, in this case, how was that? A few 10⁻⁷, I believe, or no, even larger than that, solar masses, you think of something huge. But the truth is that, for instance, in the case of our Milky Way, if you think of the supermassive black hole that is sitting at the center of our galaxy, that black hole influences things. So it influences the motion of things out to a radius of about 3 parsecs. A parsec is a unit, something like 3.3 light years. So say, more or less, things move around the supermassive black hole, influenced by the supermassive black hole out to a radius of 3 parsecs, which is about 10 light years. Now, 3 parsecs is a unit. Again, you can call it anything you want. You can call it a cucumber. It's just a unit. So the black hole affects things within a radius of 3 cucumbers. But a galaxy has a size of thousands of cucumbers, actually tens of thousands of cucumbers. So from the point of view of a galaxy, a tiny black hole is something microscopic. It's something that you can ignore. But for some reason, which we do not understand yet, the evolution of the whole galaxy, of that monster, and the evolution of that mosquito is linked, and we don't understand why. But anyway, this is an observation of the M87 galaxy. And this is actually, I stole this from the comic XKCD, which is very fun. And contrary to the usual thing, in which they say this is not to scale, this is to scale. So this is the solar system, that's the sun, we're around here. This is Pluto, and this is how far the Voyager 1 has got since it was launched. So it is difficult to explain this shape at the center of a galaxy without, invoking the existence of black holes, because this looks black to me. Anyway, until that observation by the Event Horizon Telescope, I used to say that the supermassive black hole in our galaxy was our best candidate. Now I would like to call it our closest candidate. And this is so because for about 20 years, astronomers, so people doing astronomical observations, they have been taking their telescopes and pointing, towards the galactic center. And they take a picture, and then they take another picture. They wait a couple of months and take another picture. They wait a couple of months and they take another picture, and so on and so forth for 20 years. So why do you think that they do such a thing? Because they are bored? No. These are very smart people, and I am very happy to call many of them very good friends of mine. And they have been doing that because they have seen something which does not make sense. When you look at the galactic center, stars do something that they should not do. And this is again a question that I like a lot to ask students. So what doesn't do a star during the human life of a person? So during the lifetime of a human being, a star does not move. Now, if you look at the galactic center, I don't know whether you can see, but I am hand waving all the time. If you look at the galactic center, Alejandro, can you see me?
Yes, Pau.
Wonderful. because I don't know, it's like I'm talking to, to a black box. So if you look at the galactic center, there is a radio source which they have called Sagittarius A star. To have time to explain why that star thing. But there is a bunch, and I mean about 100 of stars distributed around that supermassive black hole, and they are doing something which they should not do. They are moving, and they are moving on time scales of about months. Now, if you try to explain why they are doing that, the only way is to, assume that you have a potential well at the center of the system if you want to respect the orbits of the stars that you observe, because you observe them, right? You know your Newtonian gravity with some tiny relativistic corrections. You know Kepler's law, so you have a distribution of a few orbits. There's only one of them which is completely closed. They have actually, that orbit has gone through periapsis and apoapsis twice. So you have two periods around the orbit in 20 years. And if you want to explain the motion and distribution of the Hamiltonians that describe that system, so eccentricities, signature axis, masses, etc., then you need a point particle which has a mass of about 4 million of solar masses, with a volume, I said a point particle, that's wrong, with a radius of about 22 million of kilometers, if I'm not, yes, 22 millions of kilometers. Now, this is about 1/3 the distance between Earth and the Sun, which might seem like a lot, but is nothing, again, compared to the size of a galaxy. So why I'm telling you this? I'm telling you this because when you look at the galactic center, you have a problem, and the problem is that we are on the disk of the galaxy, so that you're facing a lot of stars, a lot of dust, and a lot of gas, which obscures your observations. And trying to work with light is a nightmare because it gets absorbed and it is very difficult to get any kind of observation. It's actually a wonder they have managed to do what they have accomplished, because you only see 5% of the brightest stars that you have over there. Anyway, gravitational waves do not have this problem, because if you remember what I said at the beginning, these gravitational waves are a kind of perturbation. So it's the way space-time is perturbed. And because matter is embedded in space-time, there is almost no way for you to obscure those gravitational waves, which makes the universe transparent to us. So why is the study of black holes interesting? Well, for me, this is particularly interesting because it is a way to probe gravity, because we don't understand gravity yet, or still I don't understand gravity yet. So in mathematics, so this is the usual, I don't want to make this too technical, but in a space-like diagram, this would be the motion of an object along a long time. This axis here is time. And this could be, for instance, the lifespan of Alejandro. The important thing, for reasons that I don't have time to spend here, is that this slope is not higher than 45 degrees, because then Alejandro would be moving faster than the speed of light. Anyway, a singularity is not a point in the space-time where gravity becomes infinite. That's simply wrong. And this is something that people keep on explaining again and again and again. And actually, if you go to the Nobel Prize document for the Nobel Prize Award to Roger Penrose, Genzel, and Gates. You see on the first figure of that document, you see a black hole depicted as a circle with a point at the center of the circle, and they describe that as the singularity. If your black hole is Schwarzschild, the singularity is not a point and where density becomes infinite and so on and so forth, like in the Big Bang. So these pictures where you have this little point exploding and you have the universe inflating from that point, these pictures are wrong. Because a singularity, at least in the case of Schwarzschild, and anyway, I don't want to get into details, but a singularity is something, it's not a point in space, it's a moment in time. It's something that will happen in future. So if you fall into a black hole, geometry around you, this is a geometrical problem, geometry around you will squeeze you to death. But it's not that you reach a point in which, a spatial point where density is infinity and so on and so forth. It is actually, we define a singularity in general relativity in a given spacetime. So a spacetime is singular if it's inextendable, so that you cannot embed it as an open set of a strictly large spacetime. This is a very complicated way of saying the picture about the Big Bang does not make sense, because if you think about it, the Big Bang is the beginning of space and time. So where is that point located in those pictures, if it's the space and time itself? Anyway, yeah. Yes, and you have to admit, of course, a causal curve. This is what I was talking about, the 45 degrees before. Now, some examples of singular spacetimes. For a Schwarzschild black hole, as I was saying, every future extension of a particle falling inside the event horizon must reach a singularity in a finite time. In the case that you have a Friedmann-Lemaitre-Robertson-Walker spacetime, this expansion factor A, which comes here in the metric, vanishes in a finite time when space-time is incomplete. And this is actually the proper definition of the Big Bang. But yes, there's a finite past. If you think of the Big Bang, it is not a point that was in the past, it's a moment in the past. Anyway, so just let me complete. I know that this is going to mathematical probably, but so the fun, interesting thing is that the interpretation of incomplete world lines, so the life of Alejandro in this space-time, is not clear yet. So you could have, if you had an incomplete causal curve, you would have a finite past or a finite future, or both. Okay. And what happens beyond that is, well, it's anyone's guess, because that thing is not embedded in your manifold anymore. It's outside of your, it does not make sense to ask that question, because we don't have the physics for that, and we don't understand what geometry is beyond that. But anyway, the interesting thing is that this is not an academic exercise. This is not just, and excuse, as they say in English, excuse my French, this is not mental masturbation. This is something deep, because the appearances of singularities in real, so realistic spacetimes is fairly common. And the conditions of these theorems are of the same form. There is the positivity of energy, the existence of horizons, and causality. And actually that allows you to connect the geometry with topology, okay? Because the integral of the curvature of a manifold is 2 pi its Euler, in German, Euler characteristic. So that you just need to find one geometry. You know that, for instance, on a plane, on our world, the sum of the angles of a triangle is 180 degrees. But anyway, let's move on back to physics now. So the important thing is that you can link geometry to topology, and this is amazing. So stream mass resonance spirals. Let me explain you something, because I'm actually running late. So I'm going to probably stop the share and explain something with my hands. So the important thing is that, so if you have a supermassive black hole, and you take a star like our sun, and you throw that star towards the sun, towards the supermassive black hole, that sun is going to be totally disrupted. Now, if you take a compact object, instead, a small black hole, a neutron star, or a white dwarf, that compact object is so compact, you have to think that, for instance, if you take one sun and half of another sun, and you compress it to the size of a city like Barcelona, you have a neutron star. So it's something extremely compact. So this thing, because it's so compact, can withstand the tidal forces around the supermassive black hole. Because it's on a bound orbit, it will go to apocenter and come back at pericenter. But in this process, the thing is going to lose energy in the form of gravitational waves, because we are perturbing space-time. And that loss of energy leads to a shrinkage of the symmetry axis. But there is more than that, because the orbit is going to precess like Mercury on our solar system. And by the way, a lot of people don't realize that the precession of Mercury is of about 98% Newtonian, and you only need that little tiny bit of relativity to explain the full precession, which was the reason why special relativity was so impressive, because Albert Einstein managed to explain the full precession. So you have a precession of the orbit, and if this supermassive black hole is spinning, which means that it's rotating, then you will have a basculation of the plane of the orbit. What does this mean? This means that means that the small compact object is going to get close and then far away, close and far away. And every time, so all along the orbit, it is emitting gravitational waves, but it is at pericenter. So when it gets very close to the supermassive black hole, we have a very strong burst of radiation. And that radiation contains a lot of information. Now, how many cycles do you have? You can prove that you have as many cycles as approximately the mass ratio. So if here you have 1 million, and here you have a mass of 10, then you have 10 to the 5 cycles before this small black hole falls into the supermassive black hole. Now, because you are, shrinking the orbit, you are precessing the orbit, and you are changing the plane of the orbit, you're getting one picture of a space-time here, of a space-time here, 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 here. So what you're doing is like having a camera taking pictures of a space and time all around the supermassive black hole. And not just a few, we have 100,000 of them typically. So I'm going to share the screen now with you, and I'm going to show you, wait a moment, I'm going to show you a movie, which is here, so that you understand what I mean. And that movie is here. Not this one, sorry, but this one. I'm trying to speed up a little bit because time is running very short. Okay, share screen. No, not this one. Share screen, and this one, and share with some. So you are going to see now a simulation, a numerical simulation of a small black hole flying around a supermassive black hole. Okay, and this is the the thing. So on the center, you have a supermassive black hole with a mass of 3 million solar masses. This is the small black hole. This is how many days you have before the small black hole, crosses the event horizon. And here you have the average speed of the system, which is 20% the speed of light. On the bottom, you can see one of the two polarizations. And I don't know if you can follow my cursor, but you see this peak here. That peak here corresponds to a burst of gravitational radiation when this small black hole was very, very close to the supermassive black hole. Now, this peak here is approximately what LIGO and Virgo have been observing so far. And they have required decades to develop the tools to solve Einstein's equations to get to one of these peaks, which lasts for about milliseconds. We're not talking about milliseconds now. We're talking about years of data. So reproducing these waveforms is going to be, and is already, very challenging. And the truth is that we don't know how to do it. We want to hear now, actually, the gravitational wave, because this person, Steve Drasko, friend of mine, enhanced the frequency by so and so many octaves. So this is how it goes. You see that the structure is becoming more and more complex. Let's jump forward. You also hear how it increases in frequency. It goes up, and this is becoming more and more complex. We go here to about 180 days before the measure. It's even more complex. You will see now some resonances forming here because we have 3 fundamental frequencies. And whenever you have a particular combination of them, you build up resonances, like I think, yes, like this one. And when you get to 0 here, what do you think that is going to happen? Look at the structure of this wave. By the way, I just said that we don't know how to simulate these things, and I am showing you a simulation. So probably you might want to ask me why. So this is 7 days. And then when we hit here 0, the following happens. Oh. So there is a cut of information because, the small black hole has crossed the event horizon of the big supermassive black hole. Okay, now I want to share the screen, and I'm going to do that. I'm going to actually speed up, share, and then view full presentation somewhere, but I don't know where this is now. Yes, here. Okay, I'm going to speak. So the important thing is that there has not been any other mission conceived, planned, or even thought of ever that can do the kind of science that you can do with these extreme mass ratio spirals. They are called extreme mass ratio because the difference in mass ratio is extreme, and they are in spiraling. So you can actually test general relativity because it's a theory. It's a very good theory, but it needs corroboration. It will. So the word line of an extreme mass ratio spiral gives you a geodesic of a space-time, so that it allows you to probe geometry of a space-time. And yes, it allows you to test alternative theories of gravity, etc. But it also delivers information about the astrophysical, so redshifted astrophysical parameters, such as the mass and the spin, without any modeling other than general relativity. So this is a direct reading of the value of the redshift mass with an error between 1 and 0.1%, and of the spin of the supermassive black hole with an error between 0.01 and 0.001, I think. So extremely tiny. Anyway, let me speed up. So the question is, can you detect them? And yes, you can detect them because we have an interferometer which is going to be launched into space, which is similar to what LIGO and Virgo are doing, only that instead of a few kilometers, we have 2.5 million kilometers between the 3 satellites. Inside of this satellite, you have a free falling mass. And now you need a resolution of 1 picometer in those 2.5 million kilometers. And because, you know, because this costs a lot, it's something like 1,000 million euros. And I always say that this is extremely expensive. This is the equivalent to 2 Spanish football leagues. And I actually took the time to check for it, and it is not. It is about half the cost of 1 league of Spanish football. And yes, well, anyway, I will leave that there just as a comment. ESA required that we can do from a technological point of view what we claim that we can do. And we can, because the so-called LISA Pathfinder was launched, and this is something like the strength, if you want, but this is actually this is a differential acceleration, and as a function of the frequency, these were the requirements of the LISA Pathfinder. This was the first thing that they got in April 2016. These are the requirements of the full LISA mission, and this is how good they got it in February of 2017. So we can do that. And I'm going to skip this just by showing you 2 slides and the conclusions. The point is that you don't have to wait 15 years to detect captures, because recently, well, actually in 2018, I showed that you can, I'm going to skip all of this. Sorry, I'm going to leave it here. No, where is it? Yes, here. So I was talking about intermediate mass black holes at the beginning, and you have a very similar process in globular classes with these intermediate mass black holes. Those black holes have masses between, say, 100 and up to, say, a few 10 to the 4. Now, this is a strain, this is frequency, this is the LISA window, this is the LISA experiment, and this is LIGO math. And these are different harmonics corresponding to the gravitational wave of one of these intermediate mass resonance spirals. From this triangle here to the merger, it is 1 year of time. What does this mean? Well, this means that if today is the 7th of July 2021, and LISA was operational, LISA could tell LIGO, look, in 1 year, so in, I don't know, say on the 6th of July 2020, at 3 p.m., 15 minutes, 20 seconds, and so many tenths of a second, you will have a system of 2 black holes of masses blah and blah merging at exactly this frequency with an eccentricity of blah and blah. So please get ready. They can optimize their instrument and break up degeneracies, because you have information about the merger and the ring down here, and you have information about the spiral here. Okay. Anyway, I'm going to skip all of this and I'm going to go to the conclusions. So, gravitational wave and candidate black holes, a check mark list. So, have LIGO and Virgo directly detect gravitational waves. This has been done. Detect merging black holes has been done. Detect inspiraling neutron stars. This has been done. And the associated electromagnetic counterpart, this has been also done, so that you have opened up multi-messenger astronomy. And this is a very important word if you want to, write a proposal these days in astrophysics. We have done sub-femto G measurements with the LISA Pathfinder. This has been done. So that LISA has, for the first time ever, a firm launch slot at LISA, because with help from NASA, because LISA was always 10 years in the future, regardless of the moment in which you were talking. You have got a Nobel Prize, 2017. You have seen the event horizon of M87, thanks to the Event Horizon Telescope. Got the 2020 Nobel Prize, and the most important thing, the last point, which is coming here, and you can guess. So I have been working on gravitation and gravitational waves for the last 16 years of my life, and all of this has happened in the last 5 years or so. So you can imagine that this is extremely good news for me. But much more important than all of this is the last point, which is to get fashion involved in gravitational waves. Look at this. This is a hoodie that I saw at the Gangnam Station Underground Shopping Center in Seoul in 2017. And look at that, gravitational waves. So this is the proof that you are on the right track and that the future is bright. So that was it. I'm sorry for talking a little bit too much, and thank you.
Thank you, Pau, for this very nice Law Physics webinar. Before checking the YouTube and the possible questions, I want to know if someone in one of the coordinators have a question. Check.
Yeah, Alejandro, I have a question.
Go ahead. Yeah.
Okay. First of all, Paul, very nice the webinar. I like it a lot, especially all the kind of the landscape of everything that is happening in gravitational waves with black hole and everything. So one question that I was wondering, because usually when people talk about black holes, there are these 2 or 3 categories, that is Schwarzschild or rotating black hole. In these scenarios, when you were discussing that you have 2 merging of black holes, in when one is rotated against the other, this is the final black hole tend to be just a rotating black hole with some characteristic, or it still has to be more refined measurement to distinguish between rotating or not rotating?
So I would say, the spatial solution of Einstein's equations are the solutions of Einstein's equations in vacuum, assuming spherical geometry, which, in my point of view, it's like they have some problems, because it's like the black hole has been there always since the beginning of the universe, and this is not the case. We know that the black holes form, and to have this thing which is so fashionable now these days about primordial black holes, etc. But usually a black hole forms out of the collapse of a star, right? In that case, in nature, it is, I would say, it's virtually impossible to find something which does not have some angular momentum. So that in that regard, this spatial solution might be envisaged as a kind of idealized, or if you want, equilibrium or solution of the more general solution, which is the Kerr solution, right? And spatial black holes are nice because they have singularities which behave in a way that we understand and can predict. Kerr black holes, so non-perturbed black holes, so rotating black holes, have these naked singularities, which per se are not a problem. But the problem is that in spite, so you have the event horizon, but if you, Roberto, were to cross the event horizon of a black hole, which is Kerr, later you would encounter another horizon, which is called the Cauchy horizon. And we have a very big problem, because once you have crossed that inner horizon, predictability breaks down. So general relativity cannot give you an answer as to the dynamical evolution of your world line. But going back to your question, when you have it is basically impossible to have anything. I'm talking like an astrophysicist now. In the universe, you don't have anything which is purely spherical, symmetric, non-rotating, and in vacuum. So we can forget about the Schwarzschild.
I think there's a question in YouTube from Samuel Bueno Soltao. So, okay, he says, congratulations on the original and exciting talk. And he wants you to comment a little bit more on the singularities as being a point. And then if you have like an alternative way of thinking a Big Bang singularity, Pau.
Yes. Yes, this is actually a question that I like a lot, and I could talk for another 1 hour if you want, but
please don't.
But so I like the common singularities in quotation marks, because when you say singularity, because of so many movies, and most of them from Hollywood, we are extremely confused about singularities. So singularity means something, it's a synonym to saying, I don't know what happens here. So you could replace the word singularity from all general, this is of course my personal opinion, you could replace the word singularity from all textbooks and replace it with I don't know what is this, and it would be a much more precise term probably. But mathematically, of course, you can very precisely define what is a singularity. Now, in the case of Schwarzschild, as I was mentioned before, the point is that you are working on spherical coordinates, and that in that case, if you look at a conformal diagram, which is anyway, it's a way of looking at it's a way for you to solving Einstein's equations without having to do the mathematics. You can draw lines here and there and understand a little bit of relativity. When you cross the, so what's the name of this guy?
Samuel or Samuel.
Samuel. Okay, Samuel. So if you cross the event horizon of a spatial black hole, you would notice nothing at the beginning. Only that if you looked around you, and if we idealize you and you were a point particle, everything around you would look the same, which is why we say that the interior of a spatial black hole is isotropic. But because you are moving on a world line, geometry all around you would be very, very rapidly evolving. But at some point in your future, you would meet the singularity, which is nothing else but the end of space and time. Now, if instead of Schwarzschild you had Kerr, rotating black hole, then something extremely interesting happens, because you know that, for instance, if you have a droplet, a drop of water in space, and you give it some momentum, you make it rotate, that spherical distribution will become more oblate, right? Because the thing will get oblate, and it will be like this. When that happens, you're talking about Kerr black holes, and in a Kerr black hole, the nature of the singularity is much more complex, and you can define it using two angles, because we're still talking about the spherical coordinates. You have phi and theta, so that if you are good enough so as to choose a given theta and a given phi, you could actually cross the singularity without having any problem, because the singularity, it is a place, it's not a moment, and it looks like a ring. It looks like a ring. So Samuel, you could, if you were, if you could have time to make the calculations very quickly on the fly towards the singularity, you could actually cross it without any problem. Now, you could cross it in spite of this singularity not belonging to the manifold in which you are embedded, which is amazing. I can keep on talking, but I guess that I should stop.
Thank you, Pau. I see
Can I make
another.
a
Yes,
question?
please, Joel.
Yes. Thank you very much for the talk. It's been very, very, very nice. So if I understood correctly, LISA can work as an early warning system of a merger. Right?
It's much more than that. Yes.
Right. Yeah.
But that's because I am extremely biased. The point is that with LISA, so again, now I am, as they say, I'm taking off my my mathematician hat and putting back again the observational astronomer hat. So the advantage of LISA is that you have years of data, and that's the advantage. And then there is general relativity, and general relativity is a double-edged sword. So from the one side, you get extremely high precision. You know that in astronomy, we usually are happy if we get things within one order of magnitude, so that 100, 500 is more or less the same. But because you're using general relativity, you get ridiculous errors. But that requires that you know what you're doing, because otherwise you will miss the observation. And one thing that I did not mention is that in a very rough way, the wavelength of these gravitational waves are, so in order of magnitude, are comparable to the arms of your detector. Now, because LIGO is measuring the merger of binaries of black holes, which are about to, merge, you're fine on Earth, because that wavelength is of the order of kilometers, so that they last milliseconds in the band of the detector. When going to space, something different happens, because you have wavelengths of millions of kilometers, so that you can measure the system, first of all, for years, and you go to masses which are completely out of reach for LISA, talking about masses of 10 to the 5, 10 to the 6, and maybe a few 10 to the 7 solar masses. And this is impossible to do from the ground.
Right. So, but still, I mean, still in the frame of giving information for the ground-based systems. I was wondering if you're having because the animation that you showed gave us a time scale of about 1 year or so, right? Mm-hmm. So I was wondering if you're having many of these events happening, how well is your resolution of saying, okay, in this direction, these are maybe we need to triangulate. Should we have many LISAs going around? I was wondering about that. Can we say, okay, this is going to happen here.
Yes. That's actually just I didn't understand you. So sorry, and that's a very good question. No, it was my fault. That's a very good question. So having many LISAs flying would certainly help. The problem is that you have to convince Spanish people to give up football for a couple of years, and they will not do that. But in any case, so there is a problem here. So if, for instance, these events are probably very rare. So if we launched LISA today, and we looked at our galactic center, we would not see one of these, because you can actually estimate, analytically with a pen and paper, which is probably the best thing to do things, the best way of doing things. you can estimate that you have one of these events every 100,000 years, if not every 1 million years. Now, that's not a problem, because I didn't mention that. It was in the slides, but I didn't mention that. With LISA, you can see these events being extremely pessimistic out to a redshift of 1, and being very, very optimistic out to a redshift of 4. So that you have millions and millions and millions of galaxies. Now, if only 1% of them, say, of these galaxies have one of these events when LISA is flying, because LISA is going to live, say, for between 5 and 8 years, then you're going to catch a lot of them. That's only a partial answer to your question. And then there's a problem, because we're talking about gravitational waves. And in gravitational waves, we don't have information about the redshift. So we know that we can detect them out to a redshift of, say, 2. But when we measure it, the only thing that you're going to see is the signal to noise ratio. And then you can get confused and say, so was this an event happening at a redshift of 2 with a mass of A, or was it an event happening at redshift of 0.5 with a different mass? Now, there are workarounds, like if you have a galaxy survey and you have enough galaxies, you can kind of localize the event. That's one problem. The second problem is that when you do data analysis, and data analysis for LISA is almost a different, a new category of science, there is a degeneracy in the parameters that you don't know whether the source was on this direction at a redshift of, say, whatever, or in that direction. So there is a 180 degrees degeneracy. So ideally, you would have to rely on an electromagnetic counterpart, but something, associated to the event, like, for instance, this stellar mass black hole crossing an accretion disk and flaring electromagnetic signals. But on the other hand, that would deviate the orbit of the extreme mass transfer spiral so that it would not correspond to a vacuum solution of general relativity. Alejandro knows a lot about these things, and he knows that these things are a nightmare. So yes, that's my answer. So fortunately, it's not an easy thing, because that means that you have to think about it. I was actually very disappointed when they announced first detection, because it was too much of a textbook. It was what the people had been predicting for decades. It was actually boring. If the signal had went in a completely different direction, that would have been fun.
Right. Okay, thank you very much. It's been
thanks to you.
Very, very interesting.
We still have 2 questions, but we are running out of time. So please, short questions. So the first one is by Vikram Keshari Parida over YouTube. He's asking if we can have gravitational wave from binary Reisner-Nostrom black holes, charged black holes. And he then makes a follow-up question, I guess, is like, what kind of gravitational wave do we get from those systems?
Yes. So there's a conceptual problem here, because black holes, contrary to, for instance, Roberto, are extremely simple systems, because you can describe them with 3 numbers, right? Mass, spin, so something like angular momentum, and the charge. Try to describe Roberto with 3 numbers. You cannot. It would be impossible. So these are 3 fundamental quantities. But the problem is that in principle, although you can find many different, you told me that I should be quick. In principle, if a charged black hole accretes a little bit of something, it will be the charge, so that charge disappears. It's like, touching, when you can have a socket and you have this third thing to avoid electrochemical things. It's the same thing. Even if it initially had a charge, you lose it almost instantly if you accrete something. And we know that black holes like to accrete things.
Great, thank you. And then the last question, I think it's also from the YouTube channel by Gabriel Gomez. Said, you said the gravitational wave can map space-time and give us information about it where possible dark matter resides. So can Lisa give us precise information about the dark matter distribution around Lisa's black holes?
Matter. It's like, I don't know what is dark matter. So what I know is that there is something that we cannot explain. And so I can give you the 30-second summary or the 2 hours speech. I'm going to give you probably the 30 seconds summary. So if dark matter exists, and I am not saying that it does not exist, and if it is distributed in galactic nuclei, and it's possible that it is so, because you can extend the Navarro-Franken-White density profile and get what they call a crest of dark matter in galactic nuclei, then we would have a problem, because that would be an additional, it would be a deviation from the pure vacuum solution of general relativity. So to answer the question of Gabriel in easy words, which is impossible, if you know what model of dark matter is the true one, because there are many different ones. Could be a scalar field, could be a boson star, or could be, well, anyway. And you know how to assess deviations of the waveform so that you could reverse engineer the observation to derive the information that you're looking for, so you need a consistent theory that predicts deviations from the pure vacuum solution. Then you make the observation, you get your results, and you compare it with your theory. If your theory does not have a billion, not a billion, but it's enough that you have 4 free parameters. If it has a very low number of free parameters, it is likely that you can map dark matter. But I guess that you have realized that I have said the word if a lot of times.
Okay, so thank you everyone for attending to this Law Physics webinar. Remember that Pau put his email and information. He actually has a very nice webpage full of stuff that are very interesting, from lecture notes to workshops that he organizes all around the globe. So thank you, Pau, for this wonderful Law Physics webinar, and for our public and viewers, let us keep in touch and wait for the next one. Thank you, Pau. Thank you, everyone.
Bye-bye. Thank you, everyone. That was very nice.
Okay.